All right, the first thing that we should discuss is that we are going to use big words that don't mean too much. It just sounds really bizarre. So we're going to talk about how our orbitals become morphed and hybridized. So we're going to learn how we make hybridized morphed orbitals. They're not going to be just plain s orbitals and plain p orbitals. They're going to morph into this special sp orbital. It's not that hard to figure out, but it is. It just sounds complex. So when we look at the valence bond theory, that means that we have valence electrons that are in the valence shell, and we try to fill octets using this. You will find that we end up not having the correct bond angle predictions that we did yesterday from our geometries. So valence bond theory states that bonding occurs when atomic orbitals overlap, meaning that if I'm going to bond, I have an atom here with an s orbital and an atom here with an s orbital, and those s's come together and then they overlap and bond. Or I have p orbitals that are going to come over and they're going to overlap and bond. When we do that, we expect specific bond angles, but we may not actually see what we're supposed to see. So these are the electron configurations of these atoms. So probably take your periodic table out. It will help you see where all the numbers are coming from and kind of keep up with the lesson. So we know that boron has 5 protons, and max that it can hold is how many? 6. Like, we can't create more than 3 bonds with boron. We know that. So BF3, if we draw our geometry from yesterday, we would kind of see what this is going to happen. We know that BF3 is going to end up with just the 3 bonds in a trigonal planar geometry, right? So we have to bond 3 fluorines in the valence electron shell. So according to this, we have boron is 1s2, 2s2, and then we go to the p orbitals, and we end up with only 1 electron in that, right? Because that's the p orbital. So how many spots are there for bonding? One spot, because you just have to remember that the way things bond is that there's 1 electron that's going to share with another electron, right? So this electron comes, and this electron comes, and then they share. These don't need to share. They're already bonded together, or in the same orbital, there's 2 electrons. So if they have 2 electrons in there, they don't have room for another electron to come into their orbital. Do you understand that? So the way that they bond is that there's room in an orbital to allow for an electron to come in and share, and then that orbital would be filled. And these are just empty. There's nothing to share, so there's no bonding that would occur in here. So each of these fluorines, if you check the electron configuration of fluorine, is 1s2, 2s2, and then 2p5. So this is how we would fill it. So each fluorine does in fact have 1 spot available in its p, we'll say pz orbital, to overlap. So they will overlap. And so what's the problem with this? Boron can only bond once according to this. And I have 3 bonds. So I have to somehow create a system that allows for boron to accept these 3 bonds. So what ends up happening is that boron enters this excited state where an electron from the 2s orbital is promoted to the 2py orbital. So this is 2px, 2py, 2pz. So 2px, 2py, 2pz. So now how many available spots are there? 3. Because this orbital can get another one. So you would get s orbitals overlapping to share. And then you would get a px and a py overlap, and they would share. So then that means that each of my fluorines that has an available spot can overlap their orbitals with boron's 3 orbitals, and then you would create BF3. Make sense? So this is what it actually will look like. If we did just overlap s and p's, this is what it would look like, and this is why I'm going to show you how it's wrong. So boron's atom is right here, and it has a 2s. If you look back at the other slide, we're bonding one of the 2 s's. We're going to bond a 2px, and we're going to bond a 2py. Remember, there's 1 electron in each of these, and then each fluorine is going to come in and bond here, here, and here, right? So s is spherical. Here it is. So I have 1 fluorine that comes and sits on that sphere to share with that electron to bond. And then here's my px going across, and here's my py, and we know that the pz orbital is currently empty, right? So x and y will make what degree angle? A 90-degree angle. So if each fluorine then comes in and bonds with a px and then bonds with a py, right here, I get 90 degrees. But what do I know from your note cards that you've made? What do you know trigonal planar is? Go back and look at the sheet. 120. I'm supposed to have 120 degrees here, and I don't. So if we use valence bond theory, it gets the angle wrong. Do you see that? So the problem here is that the bond angle is wrong. Valence bond theory says 90 degrees and a random angle for the fluorine bonded to the s orbital, right? Because we didn't even talk about the s orbital, it's just kind of sitting on there. Vesper theory, which you learned yesterday for your geometries that we're going to memorize, says 120. So our solution, how does this happen, is that we create these morphed hybrid orbitals. And that's the only way that we'll get the correct geometry angles. So when the electron is promoted, the 2s, 2px, and 2py orbitals of boron morph into 3 separate sp2 hybrid orbitals that are identical in shape and size. So they create a new type of orbital called sp orbitals. So they're going to stick them together. I'm going to show you how that works. So if we morph these orbitals together, they create 3 orbitals that are identical to each other. So they're not just a sphere and not just a dumbbell, but instead a sphere dumbbell morph together. And when they morph together, then the 3 of them create the bond angle for each of the fluorines to come and sit in here. And you'll get the correct bond angle. So the 2s and the 2p orbitals morph into 3 identical sp2 orbitals. So let me show you how this happens. I think the next... let me show you first. So for BF3, when we draw that geometry, you can see that you have how many domains? 3 bonding and 0 non-bonding. So those 3 bonding domains come from your 2s, that's empty, your 2px, and your 2py. And we saw how that was promoted there, and these are there. So these 3 orbitals that are needed for these 3 domains are going to morph into 1 part s, so I write an s, 1 part. Get it? 1 part s. And how many parts p? Just 2, because I'm only using 2 of the p orbitals, right? So then it's sp2. So this tells me how many p orbitals are morphed. Can I have more than 1 s orbital morphed? No, because there is only 1 s orbital. So s will always pair with the p's, but depends on how many p's we have. How many p orbitals can we ever have, max? 3, and then once we've maxed that, which orbital do we go to next? D, right? We could even hybridize d orbitals if needed. So the way that you're really going to examine this to know how many hybridized morphed orbitals you have is based on your domains. So if you have 3 bonding domains here, 3 domains, you're going to morph those 3 orbitals, and they're 1 part s, and then 2 parts p, which gives me an sp2 morphed orbital, hybridized orbital, that are exactly the same shape and size. So then the fluorines will come in and attach onto each of those sp2 hybrid orbitals. So this slide is showing us how that happens. We take part s, part py, part pz, and we morph into these orbitals, and then they are going to get stuck together. And so fluorine's going to come in and spend most of its time sitting on this end. And not a lot of most of the electrons here in this being given from the boron and the fluorine, they're going to spend most of their time being shared at this part of this lobe. Not so much this small part of the lobe. A little bit of the time it might end up over there. But because they're going to be over here most of the time, that's how we end up with that bond angle of 120. Yeah?
So is the ball on like the right side? Yeah, right there?
That's your part s.
Yeah, so is that where they join together?
Yes. Yep. Okay. Oops, that's the next slide, right? Okay. sp3 hybrid orbitals. So we just looked at sp2 hybrid orbitals. We can have sp3 hybrid, we can have sp3d hybrid, we can have sp3d2 hybrid orbitals. The only thing that makes it morph into more and more is the number of domains that you have. So once I get through this, it's really just like a system where you're going to count domains, and then you're going to take your orbitals and just put the correct exponent on how many domains you have. The key part is to remember that S can only have 1, P can have 3, D can have 5. So however many domains you have, it tells you how many orbitals need to be morphed, in a sense. We'll get there. So CH4, we know that the structure for CH4 is this. How many domains? 4. If we look at carbon and hydrogen, we take a look at hydrogen has 1 valence electron and it's 1s. That means each of these hydrogen has the availability to bond once, right? And there is a spot right there. But if we take a look at carbon, we have 1s2, 2s2, and then 2p2. So how many times can carbon bond? According to this, only twice, but we know that we end up with this, right? So we need carbon to bond 4 times, so we have to promote, how many? You have to promote 1, exactly right. We promote that one, and it ends up leaving open an s orbital, and then px, py, pz are available, and then my 4 hydrogens can come in 1, 2, 3, 4, and bond with those. So what kind of hybridization do you get? 1 part s, 3 parts p, to create an sp3 hybrid orbital. Make sense? It always has to start with s, comes from s first, and then your p's, and then if needed, your d's. So I had 4 domains, therefore s is 1 part, and then 3 more parts to make up the 4th domain, the 3, 4, 2, 3, 4, to make sp3 hybrid orbitals. So then they're all available for bonding. So here are our bond angles. What do we know the bond angles are? So look at your geometry sheet. You have CH4 once you bond them. If you haven't memorized your geometries, which I expect that you haven't, what should the bond angle of the tetrahedral be? 109.5, right? So if we do this, we get the bond angle correct. If we don't do this, we end up with incorrect bond angles. But here we see that the sp3 hybrid orbitals create this structure all the same, right? But if we didn't have them all the same, we would have 1 part s and then the parts p, and they would be different. So there would be an s sitting close here that's spherical that wouldn't give us the bond angle that we need. So all 4 of them are the same, giving us the correct bond angle. All right, building water. Water. Each hydrogen, 1s, has 2 available spots, and oxygen does, in fact, end up with 2 available spots, right? So it appears as if valence bond theory would work for this one, because we have the px and the py, or I'm sorry, py and pz orbitals that are available. But what ends up happening when you do this? What bond angle do you predict? What bond angle do you think you predict? Px and py and pz, they're all at what degree angles to each other? 90 degree. If you end up with this, look, this comes in, here's your px, your py, your pz, your hydrogens come in to bond. Here they are bonding with your pz and your py. They give me a 90 degree angle. What is the bond angle of water? Nope. Look at your stuff. Come on. It does not. So water has 2 bonding domains and 2 non-bonding domains, and it's bent with a bond angle of what? Yes. Do you get that, Allison? Yep. So we would end up again with the wrong bond angle, right? So we have to, again, even though valence bond theory worked in this system, we still have the wrong bond angle. So we have to hybridize our angles. So valence bond theory predicted 90. Our Vesper theory predicts less than 109. You don't have to memorize 104.5. Just less than 109 is appropriate. The orbital shape must be wrong. Shared electrons are not spending enough time with the hydrogens. So they're spending too much time. It's just the p orbitals that they're spending on is not in the correct location. So again, we have to create hybridized orbitals. So we have 2 bonding domains and 2 non-bonding domains with water. Let me just draw that for you again so that you see that when you're predicting your geometry. 1, 2, and then 2. So 2 bonding, 2 non-bonding. So when we look at oxygen here, we had these orbitals originally opened. The electrons are not promoted here, but every orbital in the n equals 2 energy level becomes hybridized. So all of these, which was, we did have the 2s, and then the 2p, 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 there's 4 orbitals that all become hybridized. So I have 1 part s, and how many parts p? 3 of them. And they all morph to create an sp3 hybridized orbital. How do you figure that out without drawing this every single time? So I've been trying to direct you to like this. Remember for CH4 we had 4 bonding domains? So I called it sp3. Same thing here. How did I end up with sp3? Because I had 2 bonding and 2 non-bonding. So when you look at your domains, the number of domains, whether they're bonding or not bonding, tells you how many of the orbitals need to morph. So in this example, I needed to morph 4 orbitals. So I morphed 1 part s and 3 parts p. What if I needed to morph 5 orbitals? Because I had 5 domains. If I had 5 domains, what would it be? Yep. Yes, sp3d. Are we following this? So you count your domains. Write this down. Because this is the simplified version, right? Count your domains. Morph your orbitals. With S can have 1, P can have 3, D can have 5. You're not going to go past that. In fact, I think the most you've seen so far is that we can have 6 bonding domains and 0 non-bonding. We haven't gone past that. The octahedral is the biggest there. All right, so with our water now, if we create 4 morphed orbitals that all look the same, they're all sticking on here, we end up with these being unshared with anything, right? Their own electrons are sitting there, which is why they're sitting closer. These are drawn like to scale in a sense because they are stretched out. How is that happening? The hydrogens are bonding with them. So most of the electron spent time is over here on this part of the lobe because it's sharing it. It can certainly go over here, but it's sharing it mostly over here, whereas these two aren't sharing with anything. They have their own electrons sitting on the atom. So lone electrons sit closer to the atom, and then shared electrons are pushed further away. Understanding this? So in summary, not charge clouds. I like the word domains. If you have 2 domains, that means you take 1 part S and 1 part P. If you have 3 domains, you take 1 part S and 2 part P. 4 domains, 1 part S, 3 part. You do now 5, 6. All right, what's 5, Michaela?
SP3D.
Yeah? What's 6, Tassia? Can never have 4, because P only has 3 orbitals that exist. Do you understand that? So it's the PX, the PY, and the PZ. So once you morph these 3, there's no more to morph. D2, that's right. sp3d2. So you would take 1 part S, 3 parts P, and 2 parts D, and then you could tell, you add them up, 1 plus 3 is 4, plus 2 is 6. It's really that simple, right? So what you'll be asked to do is to draw structures, predict geometry, predict bond angle, and then to predict the hybridization. That's what it'll say, hybridization. Hybridization means sp3, sp3d2, whatever it might be. And it's as simple as counting your domains. Bonding and non-bonding count the same. Pretty simple once you just put it on one slide, okay? All right, double bonds. Each carbon has 3 domains. So 1, 2, 3, this carbon is sp2 hybridized, so is this carbon sp2 hybridized. So the same thing occurs when you have more than one central atom. You can do the same thing. And sometimes each of them will have different hybridizations. You just do it for the atom that you're looking at. So C2H4, just going to draw that up again for you, how this happens. So this carbon has these 2 available. The promotion occurs here, right? We have S and P. We create 3 hybrid orbitals called sp2. We don't need all 4 of these. Do you understand that? So even though I promoted it, I don't need all 4 of them. So what I'll end up having is 1 of them from the S and 2 from the P, creating an sp2 hybrid. You'll know that because you would have drawn this and you would have said I only have 3 domains, so I only need an sp2 hybrid orbitals. But you have an orbital that's unmorphed, and it's P, and it needs a bond, and it has an electron sitting there, and it needs to be shared. So now you're going to see that you have some orbitals that are morphed, and then you have some orbitals that are unmorphed. And that is how we create a double bond. So this is C2H4. This is that structure. And we just saw that we're going to morph 1 part S and 2 part P, but we're going to have a leftover P orbital, right? So here's what happens. We have 3 orbitals, 1, 2, 3, and 1, 2, 3, which are these 2 carbons that are exactly the same, right? And we have right here, this P and this P are bonded to that carbon, right? Because we need 3 locations for bonds. Because we have 1, 2, 3, and then there's this 4th bond here. So 1, 2, 3 come from my 3 morphed orbitals, sp2, right? Which gives me this head-to-head bond here, head-to-head, head-to-head. Head-to-head, I literally mean they're hitting each other like this. And then we have this unmorphed p orbital that gives me that wraparound, which I've been talking to you about kind of all this week, is that you get p's, because their lobes are dumbbell-shaped, where they're pulling on each other to create this, which is why when you have double bonds and triple bonds, they get shorter and shorter, because you're no longer just head-to-head, you're starting to squeeze the molecule tighter where those bonds are. So your p orbitals end up grasping each other here. This does not indicate 2 bonds. It indicates 1 bond, because p orbitals are dumbbell-shaped to begin with. So if I have 2 dumbbells, this is from carbon 1, this is from carbon 2, the electrons can spend their time anywhere in here. It doesn't mean that it's just 1 is sharing here and 1 is sharing here. It's a dumbbell. So there is only 1 bond, even though I'm showing you that it goes up, across, and underneath. So this is 1 bond here from the p orbitals. So this is, 1 of these is morphed and 1 of these is unmorphed. You will always see that when you have double bonds or triple bonds. That's characteristic. Only 1 of them will be morphed. The other 2 will be unmorphed p orbitals. So you'll always end up with, I think, it's not on my slide, so I have to write it for you. What is called, oh, it's right here, a pi bond and a sigma bond. So pi bonds are p orbitals. Let me write unmorphed. If I can spell that. Unmorphed p orbitals. So pi bonds are unmorphed p orbitals. Sigma bonds are head-to-head bonds. And I can't write specifically what they are. They're morphed bonds, but they're sometimes sp2, sp3, sp3d, they could be anything. But these are always, your double bond is always going to be from one part sigma and the other part pi. So sigmas are your head-to-head, and pi bonds are the p bonds that are overlapping. So here's what you need to know. A double bond is always one sigma and one pi. Sometimes, I'll let you write that down and then I'll chat. Sometimes students get confused with pi bonds. And so if you look at a double bond in C2H4, you may say that it has two pi bonds. But a pi bond doesn't refer to a double bond, it refers to the second bond. Does that make sense? So if I have, again, this, and I draw it, and I ask you how many sigma and how many pi bonds there are, you have a sigma here, this one I'm going to call a sigma, I have a sigma, and this one bond right here is the only pi bond because it's the second bond, not the first. The first ones are always sigma. So sigmas are head-to-head interactions, and pi are overlapping unmorphed orbitals, p orbitals. And you only get unmorphed p orbitals when you have double bonds or triple bonds. So if I draw this for you, how many sigma and how many pi? Don't call out, just try to answer that. How many sigma and how many pi? Stuart, how many sigma? 3. Brian, how many pi? 2. So I have 3 sigma and 2 pi. Anybody not understand that? So sigmas are your first bonds, pi's are your second or third. If I'm going to draw this structure, how many unmorphed orbitals am I going to have? How many unmorphed orbitals are in this structure? 2. 2 unmorphed, and they come from the 2 pi bonds. You love it? You want more of it? So, because of pi bonds, we can create cis and trans isomers. Well, you create cis and trans isomers because you end up with sigma bonds head-to-head. So the word trans literally can relate to some things that you've seen before, like trans fats. That has to do with the geometry of that molecule. So we just kind of translate that into common language. Trans fats are related to this. We'll even talk about saturation later on this year. But the trans indicates the geometry of the molecule. So I think we only have like 2 more slides, and then we're going to practice this. So when we have sigma bonds, they're able to spin on an axis. The reason is because they're head-to-head. So if I take my 2 markers, and I go like this, and I put them next to each other like this, they can spin. And whatever's on the ends of these can also spin, right? Can just spin around. But as soon as I introduce a pi bond, now I have this. I don't know how I'm going to demonstrate this. And I have this holding on to it here, and it gets stuck. It can't spin anymore. The whole molecule can spin around, but it can no longer spin on its axis. Does that make sense? So when you have sigma bonds, they can spin, and trans double bonds cannot because they have the pi bond there. So the way that I remember this, cis and trans isomer. An isomer just means the exact same molecule, same like formula structure. So if I want to write C2H4, that's not a good example. How about, is there an example on the next slide? I gotta look. There is. We'll just use the example on the next slide. Here it is. So this is cis-2-butene. I'm just going to give you a little organic chemistry. You don't need to know it, but Where does the butene come from? So you probably have heard of butane. Have you? It's in your lighter. Like if you've ever used a lighter. You've never used a lighter?
For what? I don't know.
Lighting matches, I mean candles, birthday candles.
Oh, like those lighters, not this lighter. This lighter. The one with the stick, the really long stick at the end.
A match?
No,
No,
lighter.
Oh, the grill lighter. You don't have lighters at home anymore?
No, I do.
When you like roll?
No.
Yeah, you need lighters to light birthday candles, people, or like house candles. What do you use to light your candles in your room? You have a grill lighter laying next to your bed?
Oh my
Yes.
God.
That's how we like candles.
People, there's a much smaller version of that.
Like, if my mom found out I had a little tiny lighter, like,
Yeah, I feel like we should get sketchy.
Yeah.
Bad things with a lighter.
Yeah.
like
I feel like it's
You guys are funny.
Because you like stick it in your pocket and then you pull it out when you want to smoke. So it's like.
So it means you're a smoker if you have a roll lighter.
Yeah.
Interesting. Okay. Well, we have butene, and we can also have butane. So what this means is that in organic chemistry, you use the prefix of the word here. We have meth, eth, prop, but. So that indicates how many carbons. I just did it. Meth, eth, prop, but. 4 carbons. And the ane, the ene, and the ine indicate how many bonds there are between them. So the ane is single bond, the ene is a double bond, and the ine is a triple bond. It's kind of fun. You don't need to know this. I'm just teaching you it so that you can see where it's coming from. And then if you take the 2, the number 2, it comes from the position. So this is carbon 1, carbon 2, carbon 3, carbon 4. And there's a whole system of where to number your carbons, but you'll learn that when you get to college. So right here, if I say it's 2 butene, it means that the double bond exists on the second carbon. I could also have numbered it 1, 2, 3, 4. It would still exist right here. So 2 butene means I have 4 carbons. The double bond exists between the second and the third carbon. And now that special word cis and trans is what you need to know. Cis, the way that I remember it, same side. Cis means same side. You get what I'm doing? I'm saying my really pronunciated. So cis means that they end up on the same side. So it was possibly, right, you have spinning that occurs, but once you put that double bond, it's stuck. It can't spin anymore. Because if I just had this, like this, and these on the outside here, obviously I would need one more. But that can just spin around. So it doesn't matter if there's a CH3 here or a CH3 here. It's just spinning wherever it wants to go. As soon as you put that double bond in there, it gets stuck. And whichever functional groups, these are called functional groups, CH3, because I wrote it like that just so you know, it's like this, and then double bonded, and then another CH3. We just kind of consolidated drawing all of our lines. So those end up on the same side. And then these are opposite sides, trans. So opposite sides. And again, an isomer is the exact same thing. It's still 2-butene, isn't it? It's still the same chemical formula. It's just that the geometry and where it exists varies. It's on the same side or the opposite side. Simple enough. Triple bonds. Each carbon has 2 domains. What's the hybridization? Thanks for reading the slide. It's sp. How many unmorphed orbitals are there? 2 unmorphed p orbitals. How do you know? It's a triple bond. Here's the carbon. Here's 1 domain, 2 domains. One of these is morphed into an sp hybridized orbital, which gives me that head-to-head interaction there and there. But then I have 2 unmorphed p orbitals that are here and here, and you end up with that bonding, so you end up with over here, and then another one over here.
So that's why it's greater, like, grit, right?
Yes, and then it shortens that bond, and then the strength is so much more because you have like bear hugging wrapping around here now in the PZ, and then you have some more in the PY. So you have double the strength now of that bond. Isn't that exciting when it all clicks? So this is the triple bond. So this is what we just did before. So you have carbon with 2 available orbitals. They all get promoted, but we only need 2 of them to put each of the hydrogens in there and to create our single bond there. So this carbon needs 1 and 1. This carbon needs 1 and 1. So we're only going to promote these 2, and we end up with 2 unmorphed p orbitals. And then the unmorphed p orbitals, here's a great picture of that. We have 2 unmorphed. So this is head-to-head between this carbon and this carbon. And then this is hydrogen, right here. This one's hydrogen and this is hydrogen, sitting on those. So we have 2 unmorphed orbitals for each carbon. Here's one of them, here's the other one. So this one heads-to-heads with the other carbon. And then we have 2 unmorphed p orbitals. So we have our px and our pz that are unmorphed. And so this one is the Z coming out at the board to you, and then the other part of it is like in OD's room behind me. And then I have PY here and PY, and so we create, this is one bond here, and then this is our second bond, and then I could draw behind the board the other piece of it. So it creates a lot of overlapping and hugging and makes the bond shorter and the bond stronger, bond energy increases, melting point increases, all those things. Pi bonds, sigma bonds are stronger as they have shorter bond lengths and greater bond energies. So in general, a sigma bond is stronger than a pi bond because they're head-to-head. They're closer. So I'm not saying single bonds are stronger than triple. I'm not saying that. I'm saying the individual bond itself, a sigma versus a pi, a sigma is stronger because it's closer together. And a pi bond is further apart because they're in those unmorphed p orbitals further away. Last slide, and then we're going to practice it. I think I drew this for you the other day. Benzene? Did I in this class? Nope, I must have drawn it in the other class. So what this is showing you is sort of like resonance. It is resonance. This is a very, very common molecule in the pharmaceutical world, and then they attach all sorts of things off of these groups. So what this represents is that you have a carbon attached to another carbon, 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 here. So when you don't see carbons written and you only see lines, it indicates a carbon at every corner. So if I go like this, how many carbons do I have? I don't think you can see this on the video. If I go like this, how many carbons do I have? 1, 2, 3, 4. So every corner indicates that there's a carbon present. And then we know that carbon bonds 4 times. So in this example, if I have, I don't think you can see it on here. Here, we'll do it this way. If I have here a double bond between these 2 carbons, how many hydrogens can this carbon have? It can have a total of 4, but how many comes off of this? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Are you seeing? So when you see structures drawn like this, it's common knowledge in the chemistry world that every intersection is a carbon, and if I don't draw the hydrogens, they're understood. That there should be 4 total bonds to carbon, and anything that's not drawn there is a hydrogen. So these are understood carbons and hydrogens drawn in this structure. And what this is showing you is that this carbon double bond can be resonance, can delocalize over to this other side. It just means that it's moving. So these p orbitals, I'm going to draw a crazy picture right now. We have sigma bonds here, right? So we have head-to-head interactions here. These are all head-to-head interactions. But then I have double bonds. And what is a double bond then? The second bond is what kind of orbital? Pi, unmorphed. So I end up with all of these p orbitals here, and then they begin to overlap. You can see how easy it is for them to start taking this bond and moving it here. And then they're just sharing these electrons as they're morphing, not morphing, moving around this structure. So you end up with all this bond flipping. So what's commonly drawn is a circle just to show the delocalization of all the electrons on the inside here from pi bonding. Okay? So that's what it says, alternating single and double bonds that can flip-flop. Each p orbital can overlap with 2 different p orbitals. See it? can overlap with them. This leads to delocalization of electrons, and this can be used to explain resonance in Lewis structures. So the electrons are just moving around, and the double bond, again, the second bond comes from unmorphed pi bonds, which are p orbitals. So if the p orbital's up there, it can move with this one and then move with that one. Good? You guys look thrilled. Let's practice.